All right, guys, this is lesson 5.2. This is our first day of doing it. And it's more of these identities, and so you may want to have your notes from 5.1 out with the fundamental identities, or at least have your book out and look in the back of the book where you have those listed, or there's one page where they're all listed too. But you will use those fairly consistently, so you want to have those handy. Okay, today what we're going to do is going to call verify trig identities. And again, it's kind of that same idea as section 1. We're going to take a complicated trig formula and hopefully make it simpler. And I guess the book gives a little bit of an outline here. We'll just talk about this a little bit and then see where this comes into play as we do some of the problems. It's easier just to do the problems. But the first thing it mentions is you want to know those fundamental identities. So you want to have those at your fingertips. And then when we're doing any of this simplification, start on the complicated side. We're used to in algebra and any kind of math, so here in trig as well, taking something complicated and making it simpler. And so that's generally the easiest way to go. Start on the complicated side and make it look simpler. And a couple other things here. If you've got all sorts of different trig functions showing up, if you get it down to sines and cosines, that's usually the nicest way to do it, and those are the ones we're most familiar with. If you can factor things, that's always helpful. And then this last line is incredibly unhelpful, but it's kind of my disclaimer. You try something. If it doesn't work, try something else. So these problems are going to be a little bit open-ended in the sense that I can't say here's step 1, here's step 2, here's step 3. You're just going to look at it and you might try one set of identities. It might take you nowhere. It might make it more complicated. So you have to back up and you have to try something else. And so they're a little open-ended in that sense, and that frustrates certain people. Other people kind of like that, problem-solving things. Okay, so here's a problem. This may have even shown up in the first assignment if I remember correctly, because I think I helped a couple people with it. Today, this is Friday night, and I think I helped some people Friday afternoon with this problem. We want to add these two. And you guys know to add fractions, you have to get a common denominator. So my common denominator here is sine and cosine. So both these fractions I need to put over sine and cosine. The first fraction, when I look at it, what's the difference on the bottom? Here's a sine and a cosine. So I've got to multiply the top and bottom by cosine. So now on the top of the fraction I get cosine squared. My second fraction, how did I go from here to here? Well, look, I multiplied the bottom by sine. So I take the top and bottom times sine, and now all of a sudden I get on the top a sine squared. Once I have a common denominator, I can add up these fractions, so it's going to be sine over cosine, and at the top I get cosine squared plus sine squared. And again, we're just getting the fundamental identities, but when you look at the top, hopefully that one jumps out at you. That's one of the classic, most important ones. You look at that and say, wait, that's cosine squared plus sine squared. That identity is just 1. And so I take out that, I sub in 1, and I get this final answer of 1 over sine times cosine. So I performed the indicated operation. They told me add. I added. Nice review. How do you add? Get a common denominator. And so that would be my final answer, 1 over sine cosine. And you want to generally leave your answers with sines and cosines in it, because those are the two functions we're most familiar with. Next one. Same kind of thing. The indicated operation here, guys, is squaring this out. And hopefully you remember FOIL. So I've got 1 plus tangent of theta. I hope no one was groaning. 1 plus tangent of theta, because it's 1 plus tangent of theta squared. So I write that twice. Minus 2 tangent of theta. Okay, I'm going to FOIL this out. In my algebra class, I have this boy, he likes to call it double rainbows. So I take 1 times the first one, 1 times the second. Then I take the tangent times the first one, and the tangent times the second. I'm not quite sure if you see the rainbows or not. But let's do this. 1 times 1 gives us 1. 1 times the tangent gives us the tangent. The tangent times 1 gives us the tangent. And tangent times tangent gives us tangent squared. Then we have this other part just kind of tagging along. We'll see why in a minute. Minus 2 tangent of theta. And all these problems they make so they come out nicely. Okay, whenever you have an expression like this, you want to combine like terms. Look, there's a tangent and a tangent. I'll combine those two. So I have 1 plus 2 tangent of theta plus the tangent squared of theta. Look at this, guys, minus 2 tangent of theta. And all of a sudden, you can kind of see where this problem is going a little bit, because here's a plus 2 tangent, there's a minus 2 tangent. Those go away, and I feel like I'm getting my answer. It looks like 1 plus tangent squared of theta. And again, we've made that a little bit simpler than our starting point. Hopefully you're thinking, we're not done yet. 1 plus tangent squared. Look back at your fundamental identities. That is an identity. 1 plus tangent squared is the same thing as secant squared. So we can make it even simpler. And our final answer will be secant squared. If you want it in terms of sines and cosines, you know secant is reciprocal of cosine. So you could have said 1 over cosine squared as well. Either one of those would be an acceptable answer. So we've made that as simple as possible. We FOILed it out. We combined like terms. We canceled out. We used one of our identities. 1 plus tangent squared is secant squared. And all of a sudden, a very complicated expression up here is a lot simpler down here. That is a really good math technique to have. All right, next one. Sometimes they'll ask us to factor. And again, this is such a good review. Trig is such a good review of your algebra. So think back to algebra. And if I gave you an expression kind of similar, but without trig, x squared minus 9, could you factor that? Yeah, that's the difference of two squares. Remember that? And that factors into x minus 3 and x plus 3. If you don't believe me, FOIL that back out. Or as my freshman likes to say, double rainbows. And you'll get the same thing. So the difference of two squares, if I had 4x squared minus 25, that factors into 2x minus 5 and 2x plus 5. So the difference of two squares factors nicely. Look, this is a square. 1 is a square. So they asked us to factor this, so we can. It's going to be the sine of alpha minus 1 and the sine of alpha plus 1. And that's, in terms of factoring, that's what they asked us to do, and that's what we did. You could have argued up here, isn't this a trig identity? And it turns out it's not quite a trig identity. But that wasn't the question this time. It was factor. And so we factored that as a difference of two squares. Okay, a few more of these. Hopefully you're enjoying these. Look at this. They want us to factor this one again. It's 2 cosine squared plus 3 cosine x plus 1. You think back to your algebra and imagine if you didn't have the trig functions, but it was just 2x squared plus 3x plus 1. Could you factor that? And there was different ways you may have learned factoring, and this is something we can definitely go over in class. But the method that is taught now, you multiply the first term times the last term. In my class, we call it the AC method. So you take 2 times 1 and get 2. Then the question is, how can you break up 2? What times what? So when you add it, you end up with this 3. And luckily, there's not many ways to get 2. 2 times 1 is about our only possibility. And sure enough, 2 plus 1 does equal 3. So we rewrite this, 2x squared plus 2x plus 1x plus 1. Then we group the first two terms. We group the second two terms. What do the first two terms have in common? A 2 and an x. We factor out that GCF, we get an x plus 1. The second two don't really have anything in common, so we'll just call it an x. We get an x plus 1. And now look at that. They have this in common. Factor out that x plus 1. What's left? Here was a 2x. Here was a 1. And we factored that. Oh, wait a minute. Sorry, guys. Wrong problem. That didn't have trig in it. Now come back here, and we have to do this one. But look, it's the same exact problem. Here's your 2 times your 1 is 2. You could break it up the same way. So I'll call this 2 cosine squared of x. It'll go plus 2 cosine x plus 1 cosine x plus 1. So it's the same exact problem. And again, what a nice review of your algebra. I'll group the first two. I'll group the second two. And again, it's following, hopefully analogously. Maybe you've probably written down the answer already. You're probably now fast forwarding what I'm doing here. I'll take out the 2 cosine x. What's left? Cosine x plus 1. Second one is I'll take out the 1. Cosine x plus 1. Oh, look. That's the same. Factor it out. I get cosine x plus 1 times 2 cosine x plus 1. And again, they're not asking us to simplify these in this part. They're just asking us to factor. Not an easy skill, but a really nice thing that you should review and something we can certainly practice more of. Okay, now we get to the simplify part. This is just like section 1. Actually, I think we took this problem from section 1. And how do you know when you're done? When you get a constant, so that's a number. Or if you get it down to a single trig function, then you are done. So right now in this problem, you're not done. You've got two trig functions. You've got a tangent and a cosine. What's your strategy? Well, I kind of like sines and cosines, so I'll take out tangent, and I'll write sine over cosine. I still got times the cosine, but look, cosine is like cosine over 1. You can cross-cancel the cosines, and this simplifies to just sine. And if you're keeping good notes, you realize I think we've done this problem previously in section 1, and you are correct. So you have something complicated, use some of your fundamental identities, and make it simpler. A couple more problems. Secant squared minus 1. Whenever you see those squares, one thing you got to think of is, what about the Pythagorean identities? And one of our Pythagorean identities is tangent squared plus 1 is secant squared. And maybe as soon as I write that, you say, oh, that's obvious. I can see this identity right here. Maybe it's not obvious. And so maybe what we'll do here is I notice secant squared is the same thing as this. So I'm going to come here. I'm going to sub out the secant squared, and I'm going to sub in the tangent squared of x plus 1. Because look, our fundamental identity tells us those are the same thing. So I'll sub that in. Then I have the minus 1. Then I'm happy to see, oh, look, the 1's cancel out. Based on the directions, can I stop now? Yes, I can. I'm down to a single trig function. It's actually a power of a single trig function, but that's the best I can do. You might be tempted to say, wait, isn't tangent sine over cosine? And it certainly is. So you'd have sine squared over cosine squared. But according to the directions, they want a single trig function, and so we're better off stopping right up here with the tangent of x. All right, a couple more of these. Let's see. Yeah, just one more of these. And that's where we'll stop for today. And then there'll be a little bit more that we'll add on for a second day. This one looks very complicated. 1 over tangent squared plus cotangent squared times tangent. 1 over tangent squared of alpha plus cotangent of alpha times tangent of alpha. We want to simplify this. Okay, all sorts of ways to go with this, and it was kind of fun watching people even do section 1. They have different approaches to it. But the reciprocal of tangent, we might be tempted to say, how about cotangent? So it wouldn't be a bad start. And then the second part of this, it might be obvious to some people and not so obvious to other people, but aren't tangent and cotangent reciprocals? And do you know what it means when two numbers are reciprocals? So if I said 4 and 1/4 are reciprocals, if I said -7 and -1/7 are reciprocals, the thing about reciprocals is when you multiply reciprocals, look, you get 1 every single time. Or look here, we said the tangent is reciprocal of cotangent right up here. If I cross multiply, I get the tangent times the cotangent equals 1. So a property of reciprocals is when you multiply reciprocals, you get 1. So you look back here, I'm multiplying reciprocals. I get 1. So cotangent of alpha, tangent of alpha is 1. Then I look here, I see that square, I'm thinking of Pythagorean identities, and that is a Pythagorean identity. A cotangent squared of alpha plus 1 is the cosecant squared of alpha. So I'll take this whole thing out, and I will happily sub in the cosecant squared of alpha. I am down to a single trig function. I'll leave my answer like this. If somebody else wanted to say, wait, isn't that reciprocal of sine? It is, so that would be another acceptable answer. But again, I think I'd be tempted to stop here. So this completes the bulk of section 2. There's some tricky problems in here, and I would argue the trick is not as much the trig as it's the algebra stuff. So it's a really good thing to review, especially as a second semester senior, or I know some second semester juniors too. But as you prepare for your next courses, it's nice to bring back some of this algebra, especially some of the factoring. So that completes the lesson. Hope you guys are having a great weekend.